Well, since today we continue weakly interacting BG was a gas, I decided to repeat key points quickly of our derivation. Well, as usual, we add more discussion. What's the problem we are going to solve? First of all, the Hamiltonian. The Hamiltonian is consisting of two parts. The non-interacting one, kinetic energy, epsilon k, a k, rather, a k, plus 1/2 sum over k1, k2, u over v times a dagger k1 minus q, a dagger k1 plus q, k2 plus q, sorry, 2, a k2, a k1. So we have spinless bosons with a weak interaction. What does it mean, the interaction length? Once again, we have mean distance between particles. This is R naught. And naturally, R naught is 1 over density to the power 1/3. And this R naught is smaller compared to the size of the boson. So larger, sorry. R naught should be much larger than the size of the bosons. Therefore, we have n a cubed much smaller than 1. This is a gas parameter. This parameter is dimensionless. It's assumed to be smaller, much smaller than 1, which provides us condition for weak interaction. Again, suppose that bosons interact only when they are colliding. Therefore, the potential of interaction in coordinate space, it's a spherical well. So it is u naught, some constant, if R smaller than A, where A is size of boson, and it's 0 otherwise. R is larger than A. So this is a potential, which we will keep in mind. However, at the end of the lecture, I would like to comment what happens if potential is a long range. Namely, if bosons, for example, are charged and they are interacting through very long range, 1 over R full potential. So we prepare oral formulas which will be valid even for that case. Although for most of my lecture, I will keep in mind this kind of interaction. So then uq, just in order to let you understand everything better, it's a Fourier transform ur e to the power minus I ur. So let's calculate Fourier transform for this kind of potential. So the well is spherical. So therefore, I can integrate over all angles r squared dr such a way that first of all I will integrate over phi. I have a sphere and you remember that this is phi and this is theta. I have a scalar product d phi, so it is u naught if r is smaller or equal than r. Therefore, r changes from 0 to r, right, to a. Phi changes from 0 to 2 pi. And what remains is this, minus I u r cosine theta. And of course, I have to integrate from 0 to pi d theta. Okay. So, as I said, nothing depends on phi. I have 2 pi. There is integral from 0 to a r squared dr. Sorry, question?
Should be c delta and delta. Should be c delta.
Yeah. You're right. Of course. Yeah. That's important. Okay. As usually, I will write this integral d cosine theta with sign minus, and here it is e to the power minus I q r cosine theta, and cosine theta changes from value at 0, which is 1, to value at pi, which is minus 1, 1 to minus 1, and if I denote this variable as x, here the same is x, I have a minus, and I will flip the limits of integration, so I have 2 pi u naught integral from 0 to a r squared dr, and here from minus 1 to 1 integral minus e u r x dx. So this integral is very simple. I will continue here. 2 pi u naught integral from 0 to r squared dr, and here I have e to the power minus I q r x divided by minus I q r in the limits from minus 1 to 1. I deliberately do it so detailed to see you what's going on. You note r and r here cancels out, so integral from 0 to a r dr. Then in the upper limit I have e to the power minus I q r. In the lower limit I have minus e to the power I q r divided by minus r. So you see q. You see what we have here, apart from this q, this is 2 times sinus. So we have 2 pi u naught over q, integral from 0 to a, 2 times, and here r sinus qr dr. Of course, I would like to make this integral dimensionless, so I multiply it by q square and divide by q square. So therefore I write q cube here. So what remains is 4 pi u naught over q cube, integral from 0 to the dimensionless parameter qa x sinus x dx. So although I can calculate this integral for arbitrary upper limit, let's confine ourselves the situation that we are interested in small q, namely if qa is much smaller than 1. Then of course in this limit I have sinus x approximately x, I have x squared dx, this is x cubed, so this is 4 pi u naught over q cubed, and here qa cubed over 3, approximately. Q is cancelled, so one has 4 pi u naught a cubed over 3. Of course, it's trivial, so what we have is a volume of a sphere times u naught. However, at this point, we can introduce the scattering length from uncertainty. Delta q, delta r is of the order of h, and delta r is the size of Bose. We may itself write that u naught is of the order of h squared over m a squared. This is energy. If we plug it in the Fourier transform, we see that u at q a much smaller than 1 for this so-called contact interaction, where the balls interact only when they collide. It's h square a over n, 4 pi. I will keep 4 pi here. So you see that a in this calculations, which is a geometrical size of the boson, has also the same as a scattering rate. Okay, this is what I will use in one of the expressions at the end of today's lecture. Okay. So far so good. So let me clean the board. I identify what my potential is, and now we'll proceed with the diagonalization of this Hamiltonian, which is my goal. Is it clear what we are doing? Okay. As we discussed in many details during last lecture, we have a condensation. We have a phenomenon where the number of particles sitting in the state characterized by zero momentum is macroscopically large. So we may write that the total number of particles is equal to m naught, the number of particles sitting in the condensate plus sum over k not equal to 0, ak dagger ak. We can associate the creation and annihilation operator for particles with a state characterized by zero momentum, such a way that a dagger node is square root over n node, and a node is square root over n node. You may ask me, what about 1? In one case, we should say that eigenvalue is n node plus 1, but as I said, n node is a macroscopically large number, 10 to the 23, and we don't care about 1 compared to 10 to the 23. Then we see that the processes of scattering, these processes which I depicted that way, that two bosons with a momentum K1 and K2 scatter, and as a result there is K1 minus Q and K2 plus Q are created. This is what is written here, namely the boson with a momentum K2 and boson with a momentum K1 are annihilated, so they come to the point, they interact with interaction Q, such a way that momentum transferred this way, and as a result of scattering, two new bosons with a momentum K1 minus Q and K2 plus Q are created. So the momentum and the energy is transferred in the course of this process. But as I said, there are several possibilities, namely all bosons involved in the scattering can be in the condensate, or one of them before scattering is in the condensate, then one after scattering is 2, or all of them are not in the condensate. Since we know that the number of out of condensate particles is smaller than the number of particles in the condensate, we will try to drop small numbers and diagonalize quadratic form. Okay, in order to do that, I'm repeating very briefly what I have done last time. Let's first deal with H interaction. So this is my H interaction by the definition. And if I have both particles in the condensate, which means K1 is equal to K2 equal to Q, equal to 0, then this term contains 4 operators. Each of them is of the order of square root of n node, and therefore H interaction 1 is equal to 1/2 U node over V times n node square. Okay, then, and this is the only process which involves both particle signals and the condensate. Then I can have process where, for example, K1 equal to K2 equal to 0. So these two momentums are equal to 0. What remains, H interaction 2 is equal to 1/2 sum over Q, UQ over V, n node times A dagger minus Q, A dagger V. Because K1 is equal to 0 and K2 is equal to 0. Unlike previous lecture, where I said from very beginning that I replace this interaction by interaction Q equal to 0, which was correct for the potential, short range potential, which I have chosen at the time, I would like to keep this. I would like to keep Q dependence up to the last line and see whether we can use this formula for long range interaction or not. Because it's not assumed anyway here, for example, that interaction is short range. Then, of course, I can have situation when K1 is equal to K1 minus Q is equal to 0 and K2 plus Q is equal to 0. Then H interaction 3 is equal to 1/2 sum over Q, UQ over V, again a node, and since these two momentums are equal to 0, then K2 is equal to minus Q, K1 is equal to Q, I have A minus Q, A Q. In the previous line, I have two creation operators. Here, I have two annihilation operators. And you see, of course, the momentum is conserved. Sometimes in literature, you may see the diagrams corresponding to these processes. If now I will denote as line boson out of condensate and as wiggly line boson sitting in the condensate, then the first diagram is of that sort, right? The second diagram, when I took two annihilation operators in the condensate, I have this. In the third diagram, I have other way around. And so on and so forth. So geometrically, I can put each of two lines in or out condensate, and then it will give me all possible processes. So now I start to characterize processes where one particle is in condensate and other particle in out of condensate, such a way that these are either these two lines or that two lines or these two lines or that two lines. I have four possibilities.
Because I not go to square root of n naught, so we can say that it's number or...
Yes, it is a number, precisely.
It's not operator.
It's not operator, it is number. So I replaced this operator by macroscopic number. If you don't like arrow, so this is classical field. It can be still seen as an operator, but this operator means multiplication by that number. Okay, let's consider the situation that K1 minus Q is equal to 0 and K2 is equal to 0. What I have then, that H interaction for A is equal to 1/2 sum over Q, UQ over V. Then M node, of course, AQ dagger, since K2 is equal to 0, and K1 AQ. Plot the diagram yourself for this as part of homework. It's very easy. The guess is, as I said, K1 minus Q is equal to 0. I have to replace this by Digley line, K2 is equal to 0, this by Digley line. So this one is this Digley stuff, and these are straight. So then let's do the process K2 plus Q is equal to 0, and K1 is equal to 0. Namely, I take this line. So H interaction for B is again equal to 1/2 sum over Q, U, Q over V, and node, and K2 plus Q, I replace this one, K1 is equal to 0, A dagger minus Q, A minus Q. So, now I will put these two lines in the condensate. Namely, K1 equal to 0, AQ equal to 0. Which means H interaction for C, since Q is equal to 0, it's 1/2 sum of Q, U0 over N. K1 is equal to 0. I have a node here. A dagger minus Q, A minus Q. Okay? And last, I will put these two lines in the condensate. D, K2 is equal to 0, Q is equal to 0. So H interaction for D is equal to 1/2 sum of Q. Again, since Q is equal to 0, U at 0 momentum over N, sorry, over V, everything here is V. And node A dagger Q, A Q. So that's all. You see that the only difference between these two terms and these two terms, that in one Q is not equal to 0, while in another one Q is 0. For contact interaction, which exists only at the size of the well, these four terms are identical. For short range interaction, they are not. So let's now collect all the terms and use the fact that a node is equal to N minus sum over K, A dagger K, A K. Therefore, a node square is N square minus twice this. I need to plug it in here, and it will lead to twice this term coming with opposite signs. Let me now write down the Hamiltonian. The total Hamiltonian is sum over K, epsilon K, A dagger K, A K. Once again, epsilon K is kinetic energy. Epsilon K is H squared, K squared over 2M. Plus, first of all, there is a term 1/2 U node over V times M squared. Then there is minus 2 times 1/2 U node over V N sum over K, A K dagger A K. Then I take these two terms, 4C and 4D. And of course I can replace in summation Q to minus Q because I'm summing up over positive and negative moments. So plus 2 times 1/2 U node over V. And here, without losing any generality, I replace N node by N, because the correction would be square of this term, which I disregard. Sum over K, A dagger K, A K. So these two terms, you see, cancel each other. Then I have 1, 2, 3, 4 more 1, 2, 3, 4 more term. I will write them down as these terms are identical if I replace Q2 minus Q, and of course my potential is depending on the modulus of Q, not the vector of Q. I have isotropic situation, so this is plus 2 times 1/2 sum over K U K over V N A dagger K A K. So this I collected these two terms, and now what remains then, it's plus 1/2 sum over K U K over V N, and here A dagger K A dagger minus K plus A minus K A K. This is my Hamiltonian. Okay? I will clean this part of the blackboard, rewrite the Hamiltonian then, and we will start diagonalization. So the only difference between what I have written question.
N square and not E square. You wrote the N square minus 2N.
Yeah. Look, N is equal to N node is equal to N minus sum over K A dagger K A K. K not equal to 0. This is out of condensate number N prime, which is much smaller than N. I'm interested now in the situation where T is much smaller than T node. Therefore, I square this. N node square is equal to N minus sum over K not equal to 0, A dagger K A K square. It is equal to N square minus twice cross product, twice N sum over K not equal to 0, A dagger K A K, plus sum over K not equal to 0, A dagger K A K square. What do we see here? We see the same kind of process where the particles, one particle is out of condensate. So this is twice N times N prime, while here it's N prime square. Since in the Hamiltonian we took only terms where one particle is in condensate and one is out of condensate, or both particles are in condensate, but not the processes where both particles are out of condensate, it will be the same class. And why we didn't do that? Because the number of out of condensate particles is assumed to be small, much smaller than the number of particles being in the condensate. Therefore, with the same level of accuracy, we disregard this term. So here it's approximation. Therefore, I wrote that N node square approximately equal to N square minus 2 times N sum over K not equal to 0, A K dagger A K, and plug it in there. Because we discussed it the day before yesterday, if we take the total number of particles, in non-interacting system, particles come in and go out of condensate. So neither number of particles in condensate nor number of particles out of condensate conserves, while the total number is conserving. So we would like to have a total number of particles everywhere here. Okay, more questions? I denote this term as E naught. It's just constant. Then H is equal to E naught plus sum over K not equal to 0. I'm dealing with out of condensate particles. Here, epsilon K plus U K over V times N A dagger K K K. This is this term plus this term plus let me write it twice as 1/2 if you like. 1/2 sum over K not equal to 0 U K over V N A dagger K A dagger minus K plus A minus K A K. So this is my Hamiltonian, and I would like to introduce shorthand notations. Namely, I will denote 1/2 U K over V N as beta K. So it comes here and there, and I will denote epsilon K plus 2 times beta K as psi K. So we have a quadratic form, and we need to bring it to diagonal form. Therefore, we need to mix somehow our creation in an integration operator such a way that new operators are defined. Let's do it this way. B K dagger is equal to U K A K dagger minus V K A minus K. So I would like to mix states with a K creation and minus K annihilation. The same way, the complex conjugated BK is equal to U K A K minus V K A minus K dagger. So I assume that, first of all, my functions U and V are even functions of K, namely UK is equal to U minus K and VK is equal to V minus K. And moreover, I assume that these functions are real, namely U complex conjugated K is equal to U K. And the same is for V. V complex conjugated K is equal to V K. This is my assumption. I will be looking for such functions, U and V, and as long as I find them, I will diagonalize my Hamiltonian. So my goal is to find functions U and V which satisfy this condition, and one more condition which comes a bit later. So let me write this down in the matrix form. The new vector of states K B minus K is equal to UK minus VK minus VK UK A dagger K A minus K. Okay? Is it clear that? So this transformation from old variables to new variables is known with different names. Sometimes people call it UV transformation. However, it is also known as Bogoliubov transformations. The name is given due to Russian theoretical physicist Nikolai Bogoliubov, who was first suggesting this transformation for the purpose of diagonalization of the Hamiltonian. And we will see that idea to diagonalize Hamiltonian with linear transformation. What we are doing is linear because our form is only quadratic, has very wide range of applicability. When we will be discussing magnetism and diagonalizing Hamiltonian describing interaction of spins, we will come to the same structure of transformation, which then be called Holstein-Primakov, because although idea is similar, the transformation will be nonlinear. Therefore, the linear version of it will only be approximation. And the nonlinearity of transformation for spin is related to the fact that spins are non-commuting variables, unlike bosons, which are commuting. Okay, so something is missing. What is missing? I introduced new quasi-particles, but who told me that these quasi-particles are bosons? I'm mixing bosons, and depending on the way how I'm mixing it, I can get whatever I want. Therefore, I need to impose additional condition. I want my new quasi-particles to be bosons as well. Therefore, I will request that the commutator BK dagger commutator, which is BK dagger minus BK dagger BK is equal to 1. From this point, from this condition, I will find some additional condition for U and V. Let's do it. Again, if you have a feeling that I am too slow with these calculations, tell me. This is really important, and I would like to do it step by step, that you don't have any doubts, that you don't see any logical jumps. This is one of the important methods to diagonalize Hamiltonian, which will be widely used, for example, in theory of superconductivity. The lectures which start next week, and Professor Yevtushenko will tell you how to diagonalize fermionic Hamiltonian with the same kind of transformation. So we learn first bosonic part, and then we learn fermionic part, and then we learn Holstein-Primakov. So you see that it has a lot of applicability. Okay, let me now use this postulate that new quasi-particles have to be bosons as well, and express new quasi-particles from old quasi-particles. So A old, B new. And all quasi-particles, we knew that they are bosons. Okay, I'm substituting these two lines into this one. UK A K minus BK A minus K dagger. This is B times B prime UK A K dagger minus VK A minus K. So I wrote BK dagger minus, other way around, UK A K dagger minus VK A minus K, UK A K minus b k, a minus k. So this is left-hand side. Let me now transform it and simplify it, and then after simplification, I will write the equality that the left-hand side should be equal to 1. Okay, I'm collecting term uk square. I have ak dagger minus ak dagger ak. So I write commutator ak dagger, which we know is 1 by the definition. My old particles are bosons, this commutator is equal to 1. So then I have plus vk square, this term. I have a dagger minus k minus k minus a minus k dagger. So it's a commutator a minus k dagger a minus k, which is equal to minus 1. Okay? Because when I interchange the operators in the commutator, I change the sign clearly. So this is 1, this is minus 1. So what remains? Remains the cross product. So I will write minus uk vk, open the bracket, and start to collect in term. Here, uk vk, ak minus k dagger, minus ak dagger, a minus k dagger. So it's a commutator ak dagger, a minus k dagger, which is 0, right? Since two creation operators commute, always commute. Plus, I look at this term, and clearly it will be commutator ak, a minus k. It is a commutator of two annihilation operators, which also commute. So, and this should be equal to 1. So what I see, that uk square minus vk square is equal to 1. This is extra condition which I have to impose in order to be sure that my new quasiparticles are bosons as well as my old quasiparticles. So I will put it here. uk square minus vk square is equal to 1. If I look for the moment at this matrix, this is a matrix of transformation. Let me call it as M. So what this condition tells me, the determinant of this matrix is equal to 1. Right? The determinant is uk square minus vk square. So I have determinant of M is equal to 1. Then I can immediately construct inverse transformation, how my new variables, old variables are expressed in terms of new variables. In order to do it, I have to multiply by inverse matrix. So a k dagger, a minus k, is equal to inverse matrix would be, I have to take a minor and divide it by determinant and take into account sign. So here it's uk, here the minor is minus vk. So it's vk, uk. And here it's bk dagger, b minus k. So this is how inverse matrix looks like. The only difference, instead of minuses here, I have plus there. You can check that multiplying these two matrices, I get 1. I will get unit matrix. So, what is interesting here? We have linear transformation of our operators from old one to new one and inverse one, and surprisingly, this transformation is not unitary. It does have inverse, but it is not unitary. So, the point you learn that bosons are transferred with non-unitary transformation, and so what? I mean, m minus 1 is not equal to m. Would it be the opposite case? The transformation would be unitary. It is not so, because we do transformation on non-compact objects. What do I mean non-compact? Since I have u squared minus v squared is equal to 1, let me write that uk is equal to cosinus hyperbolicus some angle theta k, and vk is equal to sinus hyperbolicus theta k. Then, of course, this condition is fulfilled. So my matrix of transformation cosinus hyperbolicus theta k minus sinus hyperbolicus theta k minus sinus hyperbolicus theta k cosinus hyperbolicus theta k, and this is m. So you see that would it be trigonometric cosine and sine, then my matrix would just be a rotation. It's sufficient to have cosinus, cosinus minus sinus, sinus, and then the determinant u squared plus v squared be equal to 1. Here I have also kind of rotation, but not a spherical coordinate system, but hyperbolic coordinate system, which is non-compact. You know, your hyperbolus goes to infinity, unlike sphere, which is compact. And yeah, so this is little mathematical detour. I will not use these properties that I'm working with non-compact transformation, but you don't need to be afraid of having unitary transformation. Somehow, some people erroneously believe, learning something from quantum mechanics, that all transformations we are dealing with should be unitary. I give you example, counter-example, and there is nothing bad in it. Okay, therefore, what I will do now, and I need this transformation in order to express my old variables in terms of new variables and request that my Hamiltonian is diagonal in new variables. It will give me yet another condition on the functions u and v. I will have a system of two coupled equations. I solve the system of two coupled equations. I will find u and v. And at the end of the day, I will find my energy, which is coefficient in front of the term bk dagger bk. So, I anticipate that in diagonal form, my Hamiltonian will be written as some constant E naught, let me tell tilde, plus sum over k not equal to 0, epsilon ek bk dagger bk. So my goal is to find how ek depends on u and v and what it is. If I will do it, this is diagonal form, I will call this ek a new dispersion, new spectrum of my problem. Because I mapped my initial problem with interaction to something non-interacting. And this is very consistent with the concept of quasi-particles, so this is the way I diagonalize the Hamiltonian. And please, please, if you don't understand the theory, if you don't understand the logic, what I'm doing, ask me questions. It should be crystal clear understanding of what we are doing and how we are doing to the technical moment. Okay, so H is equal to E naught plus sum over K. I have psi K. And now I start to, this is psi K. I have to plug in a dagger K, which comes from here. It is U K B dagger K plus V K B minus K. You see, I multiply times complex conjugated U K B K plus V K B minus K dagger. So this is my first term. And there is a second one. Plus sum over K, beta K. Now there are two complete conjugated terms. UK BK dagger plus VK B minus K plus the same with K to minus K. UK B minus K dagger plus VK B K. So this is this one. Plus complex conjugated. UK BK plus VK B minus K dagger times. It doesn't matter in which order I put. Since these operators commute, it doesn't matter how I write them. UK B minus K plus VK BK dagger. And I close the bracket. Okay? So I have almost everything. I have now to collect terms with the same structure, and then request that off-diagonal part is equal to 0. So it is equal to E node plus sum over K. And everywhere I put sum over K, it's sum over K not equal to 0. Let me collect terms in front of BK, dagger BK. This one. So, BK, dagger BK. What do I have? I have psi K times UK square, right? From here. And I have UV once and UV twice, because I will replace K to minus K here. So it is 2 times UK VK beta K. Okay? Then I have plus sum over K, B minus K, B minus K, B minus K, B minus K prime. Again, here I have psi K, V K square, and I have 2 times UK V K beta K. Then I have term plus sum over K, B K dagger, B minus K dagger of the same structure as here. What's the coefficient? It's UV psi. Let me write UK VK psi K. And again, it is twice. It is coming from here. No, it's once, sorry. And then I have UK square plus VK square times beta. Beta K, UK square plus VK square. And then, finally, I have some BK, B minus K, and I have beta K, VK square plus UK square plus VK square, plus UK VK times UK VK times psi. That's all. Let me now check that I didn't make any mistake. Otherwise, I will get incorrect result. No, I didn't do anything wrong. Now I use a commutation relations for beam and express bk dagger as bk dagger beam and write my Hamiltonian as E node plus sum over k. When I put 1, this term remains, so this is psi k vk square plus 2 times beta k uk vk. This is some constant. You see it doesn't depend on operators. It comes when I substitute 1. So here, just for those, b minus k dagger is equal to 1 plus b minus k dagger b minus k. And then I take replacement k to minus k. So then I have sum over k. It will be psi k uk square plus vk square plus 4 times beta k uk vk times bk dagger bk. This is a combination of these two terms plus sum over k beta k uk square plus vk square plus psi k uk vk times beta k dagger beta minus k dagger plus beta minus k beta k. Okay. Good. So now I have to request that the Hamiltonian is diagonalized, that the Hamiltonian is diagonal in these new variables. Therefore, I have to request that this coefficient is equal to 0. I'm writing it. So beta k uk square plus vk square plus psi k uk vk is equal to 0. And, of course, I have my previous condition, uk square minus vk square is equal to 1. So it's enough to solve this system of two coupled equations in terms of u and v, substitute it here, and then I find my dispersion image. Have you ever diagonalized Hamiltonian with that kind of transformation in your other lectures? You see that at the end of the day we come to solution of quadratic equation, and let's make observation. You see that beta k, epsilon k are positive. So all quantities are positive, just because this is kinetic energy, k squared over 2m, and beta k is potential, which is repulsive. I'm considering the Hamiltonian with repulsion, therefore both quantities are not negative. From this line, I see that psi k uk vk is equal to minus beta k uk squared plus vk squared. Therefore, and I would like to put it somewhere here, I know that uk times vk is negative. Why do I make this remark? Because in order to solve this equation, I will square the first equation, and then at the end of calculation, I will need to take a square root of my solution. And in order to take right solution, right square root, I have to remember. Okay. Then